This lecture starts off Chapter 8, which will focus on understanding how atoms come together to make molecules, and how atoms within molecules arrange themselves in space, giving different 3D structures to molecules. At the end of Chapter 7, we learned how to write out electron configurations for monoatomic cations and anions. Both monoatomic cations and anions gain or lose electrons to attain the nearest noble gas electron configuration. For example, we can see that the neutral sodium atom has the electron configuration of 1s2, 2s2, 2p6, and 3s1. To attain the nearest noble gas electron configuration, sodium can lose one electron in the 3s orbital and will become the sodium plus 1 cation with the electron configuration of 1s2, 2s2, 2p6, or a neon core. As we learned when discussing redox reactions, the electron lost by an atom or molecule typically will not go off by itself into space, but rather will be gained by another atom or molecule. In this example, we can see the electron lost by sodium is gained by a neutral chlorine atom. The neutral chlorine atom has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p5. But with the addition of one electron, chlorine attains the electron configuration of argon of 1s2, 2s2, 2p6, 3s2, 3p6. This transfer of an electron from sodium to chlorine results in a positively charged sodium ion and a negatively charged chlorine ion. Just like a refrigerator magnet, the opposite charges attract, and the two ions come together to form the compound we know as sodium chloride or table salt. Instead of relying on writing out long electron configurations of atoms every time we want to keep track of electron transfers, we have a more convenient method. Lewis dot structures, or Lewis dot symbols, are representation of atoms in ionic compounds or molecular compounds that help us predict bonding, reactivity, and structure. We'll start with simple ionic compounds today, and we'll build up to more complicated structures in future lectures. Instead of relying on electron configurations, Lewis structures only take into account valence electrons, and do not distinguish between subshells like S, P, D, and F. In the example below, we see that lithium has a single valence electron in the 2s subshell. The Lewis dot symbol is written as just the atomic symbol for lithium, with a single shell representing the single valence electron. The same can be done when applied to carbon. Carbon has 2 electrons in the 2s subshell and 2 electrons in the 2p orbital. When writing simple Lewis structures, the valence electrons are arranged in a square-shaped pattern around the atomic symbol, as can be seen in the carbon. In future lectures, we'll learn more complex Lewis structures that require us to modify this square arrangement of dots, but for right now, we'll see that all the structures that we'll deal with this square arrangement of dots around the atomic symbol. So rules for writing Lewis dot structures and Lewis dot symbols. Rule number 1, the number of dots around atomic symbols indicate the total number of valence electrons. Rule number 2 is that we place one dot on each side of the atomic symbol before pairing up. This is essentially applying Hund's rule to Lewis symbols. So remember, electrons will fill degenerate orbitals before pairing spins. So we can see in the example with beryllium, where we have 2 valence electrons in the 2s orbital, we would write it as we see here on the left-hand side with 2 unpaired electrons, so one on each side of beryllium, but not paired up on one side. That would be incorrect. We can see the same thing happening with carbon, where we have our 4 valence electrons, 2 in the 2s, 2 in the 2p. We would write it as 4 dots on the sides of a square around carbon, or we can think of it as a diamond, but we would not write it out with 2 pairs on top and 2 singles or two pairs of electrons, but instead each one until we hit up to 4 is going to be written as a single dot. Rule 3 basically says the side that you start on doesn't matter. So all the examples for boron's Lewis dot symbol are correct. So what happens when we write a Lewis dot symbol for ions? So writing Lewis dot symbols for monoatomic ions follows the exact same rules as for the neutral ions. The only difference is we need to take into account the electron configuration of the ion and not the neutral atom. And what I mean by that is if we take a look at lithium versus Li+. When we have lithium, it has the helium core with 2s1 as our valence orbital, with the 1 valence electron, which would write as the lithium with a single dot. However, when we have the lithium plus cation, we've lost that valence electron. We only have a helium core, and we'll write this as the chemical symbol for lithium. We'll put it around in brackets to indicate that it is an ion, and then we'll write the charge in the upper right-hand corner. However, you might say, hey, doesn't lithium still have valence electrons, except now aren't they in the 1s orbital? Because that would be the helium core. And you'd be correct, but for most cases, removing core electrons will require a large amount of energy, so we're looking at the second ionization energy, which we've seen before as a trend is always going to be higher than the first ionization energy. And these core electrons are reluctant to form bonds because the orbital is filled and all the electrons are paired. This is why we represent the Lewis symbol as just Li, surrounded by no valence electrons, and again the bracket and the charge to indicate that it's an ion. In a similar manner to writing out cationic Lewis structures, we see that when writing the chlorine anion Lewis structure, we write the Cl symbol and we surround it by 8 valence electrons, because what we've done now is the neutral atom has gained 1 electron to attain the argon configuration, right? However, we do not write the symbol as brackets argon with a minus in the right-hand corner. This is to indicate that we're dealing with chlorine, because remember, chlorine has a different number of protons than argon, and having Cl minus is going to have a very different reactivity than argon minus. So we want to make sure, even though we have the noble gas configuration, we are indicating that we're still dealing with chlorine. So Lewis dot symbols, and now predicting the number of chemical bonds that a compound can make. So we're going to branch a little bit off from ionic compounds to touch into molecular compounds, but it still applies when dealing with ionic compounds. So in addition to being a convenient way to represent the number of valence electrons around the atom in ions, Lewis dot structures can be useful for predicting the number of bonds a particular atom can make. This is more of a guideline than a rule, but for the first 15 elements, so up to phosphorus, the Lewis dot structure does a good job of predicting the number of bonds a particular element can make. After phosphorus, the rules begin to bend and eventually break. We'll discuss this in future lectures, but for now, let's take a look at how Lewis symbols can predict the number of bonds of a particular atom. So we have our first example of lithium. Lithium with a single valence electron can make 1 bond. So we have 1 unpaired electron. Carbon has 4 valence electrons and can make 4 bonds. However, nitrogen with 5 valence electrons we can see only makes 3 bonds. This is because we've exceeded 4 valence electron and we need to follow our square-shaped arrangement of dots. To do this, we need to pair up the electrons. In this case, nitrogen will have 1 pair of electrons and 3 unpaired electrons. It's only these unpaired electrons that can make bonds. So when we have lone pairs, or those 2 dots, right, that is going to indicate that it is not a place to form a bond. However, when you have those 3 unpaired electrons, that is where nitrogen can make a bond. So following these rules, we can see from the Lewis dot structures that we could predict the formation of compounds like lithium chloride, or CH4, which is methane, or NH3, which is ammonia. All 3 compounds exist and are stable. Lithium chloride is an antipsychotic drug. Methane, so the CH4, is the gas that you burn in your stove. And NH3 is the ammonia sold as household cleaning solution. So give this one a shot on your own. Try this. Write out the Lewis dot symbol for oxygen. If you've written the structure correctly, you should be able to see that why water has a molecular formula of H2O. We've alluded to this, but now that we're comfortable using Lewis structures on monoatomic ions, we can see that electrons are transferred from one atom to another. This transfer results in the formation of a pair of oppositely charged ions that are attracted to each other. These ions are then held in close proximity to each other by the same exact force that holds 2 magnets together. When ions are held close together by the electrostatic attraction, we call this an ionic bond. It has been experimentally determined that when ionic compounds are formed from their constituent elements, they release actually a pretty good amount of heat. So there's a release of energy when ionic compounds are created from their constituent elements. Typically, this energy is released in the form of heat. When heat is released from a reaction, we say that it's exothermic. Literally, it's Greek for exo being out, thermic being heat. If heat were absorbed by the reaction, we would call it an endothermic process, endo being in and thermic being heat. Below we see a balanced chemical reaction with 1 mole of sodium metal reacting with a half mole of chlorine gas to form 1 mole of sodium chloride. In 1101, we are not used to seeing chemical reactions balanced with fractions in the coefficients, but as we progress in our studies, we'll see that this is quite common, and especially in thermodynamics, which is the study of heat and energy transfer. We also see that the symbol delta H is written on to the right of the reaction. Delta H literally stands for change in heat, or more commonly called enthalpy, or the enthalpy change of the reaction. As we've seen before, the negative sign in front of the energy does not indicate negative energy, which we know can't exist, but rather indicates that 411 kilojoules of energy was released from the reaction, so it was an exothermic reaction. If this instead were written as delta H equals positive 411 kilojoules, it would indicate that 411 kilojoules of energy would have to have been absorbed by the sodium and the chlorine gas before the reaction would progress to sodium chloride, and that would be an endothermic reaction. So to summarize, for now, all we need to understand is that when we have a positive sign in front of the energy or heat, it's going to be an endothermic reaction. It means that the energy was put into a process. And if we have a minus sign in front of the energy or heat, it's going to be an exothermic reaction. That means energy was released by a process. And we'll see how to put this into use in the next few slides. So construction of Born-Haber cycles is a useful method for calculating how much energy is released when elements combine to form ionic compounds. So take for example the formation of sodium chloride. By breaking the reaction into separate processes, we can calculate the amount of energy released when we form sodium chloride solid from its constituent elements. Because of the law of conservation of energy, we know energy cannot be created or destroyed. So therefore, we can calculate the energy of each individual step in a reaction and then add them together. On the next slide, we'll pull apart each step and see how we can find the overall energy of a reaction, the overall energy released by a reaction. So we're going to construct a graph in which, as we go up vertically, is going to be an increase in energy. So what we see now is we have a bold bar on top, and this represents the start of the reaction. That would be right here. This would be 1 mole of solid sodium metal and a half a mole of gaseous chlorine gas. The bottom bar represents the end of the reaction, or 1 mole of solid sodium chloride. The difference between the two bars is going to be equal to the energy that is released in the process. So we can see that it's negative, that it's gone down, so energy has been released. The path we will take from the first will be first to convert all the reactants to gaseous atoms. This is going to require converting solid sodium into gaseous sodium and converting molecular chlorine gas, so Cl2, into atomic chlorine gas. Next, we'll investigate how much energy is required to remove an electron from the sodium and give it to chlorine. Finally, we'll see how much energy is released when the positively charged sodium ionically bonds with the negatively charged chlorine. So we're going to break this into a series of 5 steps. So step 1, this is indicating that we need to input, so a positive 107.3 kilojoules of energy into the solid sodium to convert 1 mole of sodium metal into 1 mole of gaseous sodium ions. And we can see that represented with the chemical reaction here, going from solid sodium to gaseous sodium. This is going to be called the heat of sublimation. So maybe you've heard the term before. Sublimation is going directly from a solid to a gas. Step 2, we can see that this also takes energy. So it's going to be another endothermic reaction. So we need to put in 122 kilojoules of energy to turn the half a mole of molecular chlorine, so the half Cl2, and convert it into 1 mole of gaseous atomic chlorine. So there's our gaseous Cl. This is called the bond dissociation energy, and it's how much energy it takes to literally pull apart the two atoms of chlorine and the molecule of Cl2. At this point, at step 2, before we go to step 3, we now have both sodium as an atomic gas and chlorine as an atomic gas. Step 3. We can see now we have the process of removing an electron from the atomic sodium gas, and turning it into a cationic gas and an electron. 495.8 kilojoules of energy is put into the 1 mole of gaseous sodium atoms, and this forms 1 mole of gaseous sodium cations. This is going to be equal to the first ionization energy of sodium, so something that we talked about in Chapter 7. Remember, when we defined ionization energy and electron affinity, those are calculated for atoms only in their gaseous forms. So this is why we needed to convert both sodium and chlorine to monoatomic gases to be able to do the Born-Haber cycle. And as a reminder, it always requires energy to remove electrons from an atom. So this process, as putting this energy in and turning the sodium into sodium cation, we're also releasing 1 mole of electrons. So where are these electrons going to go? So in step 4, the 1 mole of free electrons combined with the 1 mole of gaseous atomic chlorine. This forms 1 mole of gaseous chloride anions. Because this is a spontaneous process, it's going to release, so we have a negative, release 348.6 kilojoules of energy. Up to this point, every step, so 1, 2, and 3, were endothermic. Step 4 is our first exothermic process. At this point, in our gaseous phase, we have now 1 mole of gaseous Na plus and 1 mole of gaseous Cl minus. The next step and final step, so the 1 mole of gaseous sodium cations ionically binds with 1 mole of gaseous chloride anions to form 1 mole of solid sodium chloride. This is the electrostatic interaction, or the lattice energy, of NaCl, which we'll talk in great detail after this. Since this process is favorable, so think about 2 magnets coming together, a positive and a negative charge. 787 kilojoules, so that's our negative 787, is released, and this is another exothermic process. Overall, we can see if we add everything up, our net reaction is going to be this delta E from where we started to where we finished. If we added everything up, steps 1 through 5, we should find out that when 1 mole of sodium metal reacts with a half a mole of chlorine gas to form solid sodium chloride, we'll release 411 kilojoules of energy. So you heard I mention that term lattice energy when I was discussing about step 5, this idea that it's energetically favorable for a positively charged cation to ionically bond to a negatively charged anion. So why don't we go into a little bit more detail about that. Oh, sorry, I misread my cue. Actually, we're going to do one more process on the Born-Haber. We'll do a practice problem, and then we'll go into lattice energy. So, instead of drawing a graph like we did in the last problem, why don't we calculate the net energy change in kilojoules per mole that it takes to form Kf, so potassium fluoride, from its constituent elements, so potassium metal and fluoride gas. So try this one on your own, because I'm going to break it down fairly rapidly on the next slide, so maybe pause this lecture. But we have the heat of sublimation for potassium, so it's going from potassium solid to potassium gas. We have the bond dissociation energy for F2, so the amount of energy it takes to take 1 mole of F2 and separate that into the fluoride, atomic fluoride gas, so just F instead of F2. We see the electron affinity for F, so how much energy is released when fluoride gains an electron. We also have the first ionization energy for potassium, so the amount of energy it takes to remove 1 electron from potassium. And we have this final term, the electrostatic interaction of Kf, which is going to be related to the lattice energy. So how much energy is released when a positively charged potassium ion then ionically binds with a negatively charged fluoride anion. So if we follow that through, we can go through the same steps as we did for sodium chloride. Right? We have potassium going to potassium gas, and that's releasing, it's taking 89.2 kilojoules of energy. We have a half a mole of F2 going to form 1 mole of F, and that's going to take 158 kilojoules of energy. We have now our first ionization energy for potassium. We're going to add that to the electron affinity for fluoride. And then our fifth step is that the lattice energy, that electrostatic interaction between the cation and the anion. If we add up all these processes, we get the overall energy change for our reaction, and we find out that 484 kilojoules are released for every mole of Kf solid formed. All right, so now what we're going to do is move on to discuss a little bit more about lattice energy. So this last step, this idea of the energy it takes, or energy that's released when Kf comes into contact with an F- or cation with a fluoride. But we're going to change it just a little bit. Instead of being the energy that's released when the cation and anion come into contact, it's rather measured as the energy it takes to pull them apart, right? So it's a measure between the electrostatic interactions of ions in a solid. So essentially it's calculating the strength of the ionic bond. And so a measurement of the strength would be the energy necessary that it's required to break up an ionic solid into its gaseous ions. So it's actually the reverse of what we were looking at in the Born-Haber cycle, right? So the interaction of ions to form an ionic bond is mainly electrostatic, and so therefore we can apply Coulomb's law. So what Coulomb's law describes is how two charges interact through space. So this is what we see here. There's a force felt between two particles, and it's going to be equal to this term kappa. So kappa is just a constant, and it's determined by each different ionic compound. We have Q1, which will be the charge of ion 1. Doesn't matter if it's a cation or an anion. Q2 will be the charge of the second ion. Doesn't matter if it's cation or anion. And then we have this term d squared. So it's actually the square of the distance between charges 1 and 2. So we also said that the lattice energy is the amount of energy it takes to pull apart the atoms, right? So if we think about that as a force applied over a distance to pull apart the atoms, we get this equation where U, or lattice energy, is equal to a force times the distance that you need to move those atoms so they no longer interact. Since the force keeping the ionic compound together is due to the electrostatic interaction, we can substitute F in the lattice energy equation with Coulomb's law. And this is what we get here. So now we have U equals kappa or K times Q1 times Q2 over d squared times d. Both those d's represent the same variable, which is distance, so they'll cancel out. And we're left with a simplified equation where lattice energy equals some constant times the product of the charges divided by distance. And so what we're going to do in the next couple of examples is pull apart really what this equation means and then be able to predict the strength of lattice energy of different compounds. So for the most part, we care about two distinct factors in determining lattice energy: charge, which are our Q's, and the distance between those charges, which is d. So let's first look at this. So this is a table of different lattice energies for different ionic compounds. So the cations are listed on the vertical, and the anions are listed on the horizontal. But what I want to do first is just simplify this. We're just going to look at lithium compounds. If we look closely, we can start to see a pattern emerge, right? We see as the ionic radius of the anions increases, the lattice energy decreases. So iodine is larger than bromine, which is larger than chlorine, which is larger than fluorine. All four anions have the same charge, so F-, Cl-, Br-, and I-. The thing that changes is the distance between the lithium cation and the halogen anion. And we can see as we go from left to right, that ionic radius is increasing. So this is predicted by our lattice energy equation, right? As the distance term gets larger, so our d, the lattice energy will decrease because d is in the denominator, right? What we may have not discussed before is that the distance when we're dealing with ionic compounds and even molecular compounds, when we're talking about the distance of a bond, it's going to be measured from the center of the atom or the center of an ion. So we can see here, if this is just a representation of, say, lithium chloride, we're going to have a smaller distance between the center of the two spheres than if we had something, let's say, like lithium iodide, where we have a much larger distance between the center. And that's affecting our term d down here. So the pattern that we pick up on, as the distance increases between the cation and the anion, the center of the two ions, the lattice energy is decreasing. The reason for that, right, is it's easier to pull something apart. That is going to be essentially the two charges are farther apart to start with, but when they're closer, that attraction is greater, so it becomes harder to pull them apart. Right, so when we look at the whole table again, we can see a similar pattern emerge between distance. When we look, when we follow the same, if we went across from sodium or potassium all the way to aluminum, right? One other thing I wanted to point out, but we just want to just look at the lithium column, is the difference in formal charge. And what I mean by that is the charge of the anion. So the lithium stays as a +1, but if we look at the far end, we now have an oxide anion, right? So it's not shown on the table. This is something you'd have to look up, but the O2 anion is roughly the same size as an F- anion. So that means the distance between the center of lithium to the center of fluorine is roughly the same distance as the center of the lithium cation to the oxide anion center. Right? However, we see that the lattice energy for Li2O right here, right, is roughly 3 times greater than the fluoride, the LiF here, right? We may not have been able to predict that the lattice energy would be 3 times greater, right? Because the kappa for Li2O and LiF are different, and the distances aren't exactly double, right? Or sorry, aren't exactly the same between the lithium and fluoride and lithium and oxide. But we can predict that by doubling the charge of doubling the charge of the anion, the lattice energy for Li2O would be greater than that of LiF. Because if we look at our at our lattice energy terms, we can see that we have our Q, product of the two Q's is in the numerator. So if one of those Q's increases by 2, in the case of oxide, it's going to just be greater than if you have something with a Q of equal to 1 like fluoride. So let's do a little bit of practice problems. We'll start with visualization, and then what we're going to do is switch to using the periodic table. So if we look here, so we're visualizing lattice energy strength. So we're going to be answering the question, which ionic compound has a greater lattice energy? But first, before we do that, I just want to take a second to appreciate where the name lattice energy comes from. So a lattice is a repeating structure, right? It doesn't necessarily need to be discussing chemistry. You can have a wooden lattice, like on the sides of decks or around gardens, right? It's a repeating structure that you can have a small unit that repeats over time to make a larger structure. So if we take a look only at the left compound, we'll notice that we have negative red circles, and imagine they represented chlorine, and we have positive green circles, and let's just imagine that is sodium, right? So we see that the ionic compounds are created by repeating patterns of stacked cations and anions, or lattices. So when you see a cube of table salt sitting on the table, that is because the sodium and the chloride create a cube in space, and that cube repeats on the microscopic level all the way up to the macroscopic level. And so you would actually see that cube of salt sitting on your table. All right, but let's get back to the problem at hand. So given the lattice structure of the two ionic compounds, the one on the left and the one on the right, we're asking the question, which of the two has a greater lattice energy? So first we notice the distance between the center of the positive and negatively charged circles for both compounds is roughly the same. This means that we should focus on the differences in magnitude of charge, so how big the charges are, since the distances won't be a factor in determining the differences in lattice energy, right? So if we look at our expression for lattice energy, right, distance for both of them will be the same. Kappa might be different, but we're not going to, right there we don't know. So we're going to look at the major differences between the magnitude of the charges, right? So next we notice that the compound on the left has a +1 cation, so those are the green circles, and a 1- anion, so those are the red circles, right? Since the distance does not matter in this case, it doesn't matter which of the circles, the big ones or the small ones, have the positive or negative charges. We only really care about how big the charges are, or what the magnitude of the charge is. So if we multiply Q1 by Q2 for the left component, that would essentially be multiplying positive 1 by -1. So you would get a product for the Q's as a -1 for the left-hand compound, And if we took, for the right-hand compound, we see we have a +2 cation, and we multiply that by the charge of the minus anion, we'd get a product for Q1 times Q2 of -2. So in that case, the -2, because we're looking at just at absolute values, the -2 is going to be greater than the -1, so the compound on the right-hand side is going to have a greater lattice energy. And that's solely due to that +2 charge, because the distances between the cations and anions for both compounds are roughly the same. So let's do one more example, and then we'll be done. So, oh sorry, never mind. We'll be done with the visualizing. We'll still have two more practice problems after this. So in this example, we see all the cations have a +1 charge and all the anions have a -1 charge. And that goes both for the left-hand compound and the right-hand compound. So the distance between the center of the cations and the anions are the same. Oh, sorry, the charges are the same. So we need to focus on the distances. And we can see the distance between the positive and negative charges on the left-hand compound is smaller than the distances between the charges on the right-hand compound. Because D is inversely proportional to the lattice energy, that means as D gets smaller, the lattice energy increases. So in this case, the left-hand compound is going to have a greater lattice energy because the distance is smaller than the lattice energy of this compound here, because the distance between the center of the charges is larger. So a lower lattice energy on the right-hand side, greater lattice energy on the left-hand side. Now let's try doing this by just looking at the structure, so the chemical formula for ionic compounds, and then we're going to use some of what we learned in Chapter 7 to answer these problems. So I would recommend pausing the video and grabbing a periodic table to help follow along. So first, what we should do is take stock of the ions we're dealing with, right? We have sodium, magnesium, and aluminum, right, if we're looking at the cations, are all in the same row of the periodic table. Therefore, they all have the same largest principal quantum number of n equals 3. So we're looking at sodium plus, magnesium 2 plus, and Al3 plus, and they're all going to be roughly the same size because they all have the same neon core electron configuration of 1s2, 2s2, 2p6. There will be differences in sizes, that's true. Al3 plus will be the smallest, but it's not going to be a tremendous difference between them because they're all on the same principal quantum number of n equals 3. Second, we notice that all the anions are chlorides, so that means the atomic radius of the anion is constant. So for all compounds. So again, that's telling us we only really should be focusing on the cations. So since the cation size and the anion size roughly are the same for all three compounds, that means we need to focus on the only other variable we can, and that's going to be on the charges of the the charges of the ions. All the chlorines have a -1 charge, so we should focus all on the cations, right? Al has a 3 plus charge, Mg has a 2 plus charge, and Na has a +1 charge. So therefore, that means the AlCl3 will have the highest energy, MgCl2 will have the second highest lattice energy, and NaCl will have the lowest lattice energy out of the three. So let's try one more problem, right? So this one's going to be a little bit more tricky, right? Because we're going to have ions from different rows of the periodic table, and we're also dealing with different charges. So in this case, we have to deal with both distance and charge. So I'm going to give you the heads up, when you're comparing more than one thing at once, your brain can only directly compare two things at once, so that's what we're going to do. Right? So let's first order by ionic radius and the trends that we learned in Chapter 7. So we have two potassium compounds, so that's where I would start by comparing the two of them. Right? Potassium, both of them, so the potassium cation is in the row n equals 4, right? So we're going to keep those together. Then we'll deal later with magnesium, which is n equals 3, and lithium is equals n equals 1. So since both KBr and KCl involve a 1 minus anion, we can order the two of these in terms of lattice energy, right? Kb will have a lower lattice energy than KCl because Br minus has a larger atomic radius than Cl minus. So what we already know right now is that KBr will have a lower lattice energy than KCl because Br is larger than Cl, right? So we'll order those to start with. We know that's going to be the case. So now, if we know KBr is less than KCl, so why don't we take KCl and let's try comparing that directly to LiCl, mostly because both K has a +1 charge, Li has a +1 charge, and both have the same -1 anion of chloride, right? So if we look, lithium, Li, has a smaller atomic radius than potassium, K. So therefore, lithium chloride should have a larger lattice energy than KCl because they're both dealing with the same charges. Both have +1 on their cations and -1 on their anion. So we only care about distance. LiCl has a smaller distance between the center of the two ions than KCl. So in that case, following our trends, lithium chloride should be bigger than KCl, and we've already determined that KCl is going to have a higher lattice energy than KBr. So right now we've ordered 3 out of our 4, right? The tricky one is going to come down to dealing with magnesium. Right now everything we've dealt with has a cation of +1 and an anion of -1, and then we worried about differences in sizes of the anions. Now we have a difference of charge, right? Mg2+ is in rho n equals 3, and lithium plus is in rho n equals 2. However, it's going to be difficult to compare the sizes of ions from different rhos that do not have the same charge, right? We're dealing with a +2 from rho 3 and a +1 from rho 2. With a little research, we can find out that magnesium 2+ and Li+ actually have almost the exact same ionic radius. So lithium is about 90 picometers, while magnesium 2+ is 86 picometers. With this information, we can see that MgCl2 will have a greater lattice energy because it has roughly the same distance between the center of the ions as lithium chloride does, but magnesium has a 2+ charge. So therefore, magnesium chloride is going to have a larger lattice energy than lithium chloride. And by process of elimination, essentially, we've now ordered all 4 of the compounds. So this is going to end our lecture on ionic bonding, the Born-Haber cycles, and the lattice energy.